we still have about 5 minutes, so waiting a few more minutes. Form 20 or okay, this quite a lot. Oh, okay, I know. It's okay. Yes, one more minute. Can I have one? Thank you. Okay, I think probably is the time now. So good morning, everyone. This is the last lecture, I think. I hope you enjoy the course so far. So this last lecture of mine is not the last lecture for this course, but for me, actually, it's on the application of the physics for machine learning and digital twin for additive manufacturing. And then, as I promised yesterday, it's more about the data-driven or machine learning based example that we apply to design a new material that I show you, actually nickel and also titanium a little bit by alloy design. But before that, I want to talk a little bit about what is a digital twin and what is the use for additive manufacturing. So now a lot of research has been going on to basically identify the challenge and the way how can we move forward, identify the direction strategy from interdisciplinary consortia to basically move the boundary, move the technology forward, especially for metal additive manufacturing. So if we are looking around in the a paper or in the outlet, media outlet or whatsoever, you may see digital twin like this. That's data-driven for maintenance. Actually, for let's say in a jet engine, you want to understand what happened during the operation, and then you want to have digital or physical and digital twin running at the same time to understand what is the problem during the flight. For example, that is the example that a company like Rolls-Royce trying to do it for a number of years already. It's not just happening doing it now. So the attribute of digital twin is just a virtual representation of the real world component. Again, they have some key feature that we need to understand, which is the feedback data from, and then correction of tests, and on the computer, and they provide value that you can simulate, analyze, or optimize. And this represent data of the physical asset that we are looking at here will produce a kind of perfect, hopefully, a physical product that we can use in service. But it's not just in service, but for manufacturing purpose. We may looking at something a little bit lower length scale in terms of production of the sample, for example. This is a concept of digital twin where you have a hardware here, physical twin, and you feed the real-time data, such as the data for the sensor, and then to the digital model here that you may use the surrogate model that I showed you before, machine learning predictive model to forecast or do some anomaly detection, for example, and then use AI analytical capability to feed back the real time to control and command what happened in the physical world. That we talk a lot about sensorization, about CNC hardware, software driven, or whatsoever this may be, the 3D printing machine. And this actually, we in order to summarize this, we have digital twin actually considered as a physical entity of the virtual replica in the two-way digital data that communicate each other. So that means the key is the communication between the physical and digital model, which are predictive capabilities that I will show you a little bit later what is that. And leverage this process intelligence to capture digital model using faster solving surrogate. That means what this may be replaced by the surrogate model may be replaced by, for example, reduced order is this kind of surrogate model that we have some quality control aspect of the product, for example, for the physical entity. This surrogate model create using, as I said, data-driven or machine learning. Talked before from experiment, digital model can be physics-based or statistical-based. Physics-based is what we talk a lot, and then statistical-based, probably the data come from experiment, for example, that you can feed into the digital model here. And give example of the benefit of this process, digital twin, is will deploy in anomaly detection, correction, and then diagnostics, causal process control. And that is actually what we want to do, is our vision to make it happen in the near future. So actually in manufacturing industry, so I'm trying to see some broader view and then try to narrow down to the I mean, what something related to us. So the achievement of this one or will lead to improvement of the product quality and process productivity. So using digital twin here, I mean, that means you use the digital computer for simulation and manufacturing process. This will need to understand the process, because the causal relationship will enable us to improve the quality of the product that we need. And another aspect is we need to use something, not only digital computer, also need to use digital sensor to implement digital control, because this will actually generate some data for us to feed into the model that will make us actually try to, again, as you see, the data that feed into this here will need to be from sensor maintenance history or whatsoever, that from physical model here feed into digital twin, which is, I mean, kind of digital model. Whether or not you use data analytic, machine learning, or physics-based model or statistical model here, and then you feed back your control command back to digital twin. And these will be interacting with each other. So definitely there will be some virtualize or analyze offline that you can use to control this remotely. So I see some evidence already from a lab in field lab, I mean, around the world. For example, I just visited Japan early this year, where they can control what happened, or some simple operation in the lab, which is quite amazing to run 3D printing, for example. Yeah. So another one is adopt the programmable logic control-based feedback control automation in factory, that you can actually resulting in energy scheduling, that sometime in a company in US, a steel company, that they use a digital twin or digital model to basically calculate some, a flow of material in the factory, and then try to schedule the time for the right spot for the electricity cost, that they can minimize significant number of money, I mean, in terms of millions, something like that, by actually use some digital system that they can allow this to happen. So cost reduction is the goal, and increase the productivity of the part. So now this is a bit closer, so narrow down to the kind of robotics, additive manufacturing, like arc welding, for example. You may implement some sensor and digital model here, and material model is so important, and rule models. And this is something that we feed into the data, that we can actually get some production or the machine tolerance, and feed back into the decision making into the physical entity. Again, this is, I would say, in the virtual world, or the modeling things, is the brain for the digital twin. So whether or not we can collect this on fly, that's a purpose, right? We want to do something without any defect and without any waste and wastage. Yeah. So it's quite a lot of text, but I think it's useful to highlight some of that. So you can find this information more from the journal Physics that I show you here, journal Physics material here. And another characteristic for the process digital twin for AM is actually with supervisory capability, that you can use the digital twin to offer virtual emulation or animation to support understanding of statistic or dynamic operation characteristic. For example, you can use this to plan and test the impact of critical scenario or conceptual business model. And this digital twin process, digital twin with the diagnostic and control capability, this is something is closer to us now, with the support optimization of real-world assets and process performance. And this will link to the sensor data. So diagnostics or control capability, this is actually something about sensorization, using sensor to measure it. And process digital twin with the predictive capability, this is something for the predictive simulation that we are talking about in terms of the quality control that we looked at previously. So the application of this in AM is actually start to find is used more and more now. So if we looking back a little bit, so we use predictive capability here to basically what we want to get is actually decision maker for the test and understand the impact of scenario here. What is the best, how we do it, what is a dynamic model that we can use in the real operational processes. That's pretty much the characteristic of the digital twin with different capability that give rise to different, character for the model. So this is come closer to the 3D printing. So application of what we call closed loop control. We close from digital and physical world here, and the different components that contribute to the construction of digital twin. That I think I may start from this one, which is actually not really a part of that. So you have printed part, and then you have printing machine, 3D printed machine here. So this is something you may need to run. This is a physical world and this is digital world, right? In this digital world, on your laptop or whatsoever, you have mechanistic model running the mel pool simulation, something like that, or rapid kind of calculation. And then you have statistical model. That's why I said this is the missing part that we not talk a lot in the result that we get. We just run for the sake of simulation and not actually take care of how can interpret the data. So interpretation of the data is important. And then you have a model that have a control model again. So you try to link this together. And then this is a process variable that you may try to predict to the physical world here. And data from the physical world can fade into, by sensing and control, back into the digital model. But I mean, beneath that, you will need to have the model use this one to train the machine learning, because you not be able to actually run every condition on fly. It's impossible. It has to be another layer of machine learning using neural network training here, and then you update the model and feedback. Or probably, I mean, this one maybe come from model or experimental data, large data set that you have. And then you get this simulation result feed into the data that you have here. And then trying to, or these data may come from experiment, from censoring data, testing, literature, classified data feed into this one. And again, this is still a conceptual diagram. It's not, some people try to create a flow chart for a particular scenario, but again, this is just conceptualized diagram that see how things work in research in digital twin for additive. So this one has been done, the characteristic of the application of closed loop control in this one, usually done to gain the process repeatability. Definitely now, everything is stochastic in additive manufacturing. So we need to make it actually more repeatability in the AM part here. And this will be possible for manufacture safety or mission critical part with guarantee minimum quality level. Actually, this is important. So we're not going to do digital twin for just this is digital twin. It has to be some important part that we are selected to do that. That's why I keep saying at the beginning that material process and application is come together as a package that you are looking at. So passport that you want to do. And then this is improve the product integrity for sure. And this because you don't want to reduce any necessity to cut the sample and then to see. So you want to basically, if possible, we want to do in a non-destructive testing. That is the aim, right? And we can feed the sensor back to the digital model. There's some research going on in this physical here on the sensorization of the non-destructive testing using some kind of vibration or whatsoever, that you can feed or generate the data as quick as possible to understand the defect content in the part that you have. So this is a way people doing, I mean, I'm talking about people in system engineer that they're trying to do something on in this one. So equally, the quality assurance of process product is something that we need. I mean, we need to find because this system has to be certified as well for standardization, and then, I mean, with a pass certification. And another quality control to assure quality of product is actually we need to reduce some weightage or some scrap as all possible. So ability to determine optimum process condition. Again, that's what we have been talking about the brain of this digital model here on the to eliminate trial and error experimentation. And we'll build this right first time and every time, because every time you do it, it will be right first time for that condition. So there's no longer something that this change the practice that we've done before, that we know in a very controlled manner for casting or forging. But this is quite stochastic. So that's why part will be built right first time every time. So there is another conceptual idea for digital twin that I think this is much deeper in the things that we have discussed in the past 4 days. You know that, I mean, definitely the brain of this is lying to the physical-based simulation that we talk a lot. And then, but the important part here is actually you have the physical part, manufacturing, and physical-based simulation up there. And across the length scale, you transfer the simulation validation of data flow here, and you have sensory measurement and data feedback, the loop here. Across the length scale, as I said, this is a 3D printing now in micro length scale, in the melt-pool meso, in the layer-wise, and then 3D printing level in the part or defect, something like that. So this may be an input, the geometry of the 3D printed part, powder material property, and then laser fusion parameter, monitoring and measurement here. And output will be defect content that we said before, grains, growth, and microstructure, stress and strain, distribution, distortion. And we want the output of optimized parameter. And this will be used and controlled if we can understand and then get a robust model that can give us some predictive capability with rapid calculation. We can actually, that is the ultimate goal with the data-driven that we want for 3D printing. And that actually has some kind of more specific example in the in this kind of finite element calculation here. And then you use some powder property, some way, somehow you treat in your computational grid. Here, there's some material actually heating, some material actually already heated. And then you will try to predict something that you can use pyrometer camera to detect the melt pool size, and then to compare again the simulated data from finite element analysis. So you will see here that the grid of this simulation is not good enough, but actually if it's working, it's okay, because we want to make sure that we not actually compromise with the accuracy of the of the model, but at least we can extract some important feature from the model that can predict some important things, like we discussed yesterday, that temperature field may tell you a lot of things about from porosity, as well as the property or microstructure and property that we discussed yesterday. So, but this one is not possible, only the physics-based model. I mean, I hope you appreciate that. Because they have another computer science related layer that we are talking about. So even we have here, we will have the cloud layer, which is about the data analysis here, cloud data processing and application. Again, this is a bit far from what I'm looking at, but we're looking at machine learning or big data analysis, something like that. So we are in the processing step, and then we need to link with the monitoring system. Again, this is another flow of data, and then the machine level that we need to look at, and collaborative of this data across the different layer here will be needed to be constructed to successfully deliver the digital twin for particular machine and process considered. So I think it's quite broad and give you some context about what is a digital twin and what is needed to be done to achieve to that point. But what we're going to do here, how can we actually use some application of the data driven to do something that we can get the product. Let's say input is actually the parameter composition or whatsoever, and output is a new composition. How can we actually collect or adjust the composition or apply something to additive manufacturing? I have to say that I don't have example in terms of digital twin system to show you, but I can show you some application of machine learning that we use to do something with, and then you get a product which is a kind of new powder composition that we use. So it will be based on the physics-based model that we discussed in the past few days. And this is the case for we call material design and process design for titanium alloy that we try to do since 2013. So it's a large collaborative effort. So you may know that, or may inspire from titanium is not only used for aerospace but also in biomedical application as well. So the problem actually, I think probably Professor Kumar already tried to solve it. So there's a problem that there's a big mismatch between metallic bone and because in the metallic implant we use we have the bone with different stiffness or modulus here. I mean, let's say conical bone or cancellous bone here. They have quite low stiffness compared with the organic bone, the real bone. So the way they try to do here, try to design additive, using additive manufacturing to design engineering structure that allow them to change basically the stiffness and the strength of the material that match to the bone for implant application. And this is something, if you look carefully, this paper try to show that the different design of lattices that they call meta material. Actually, this is 5-6 years ago. You will see that you can actually going closer to the real modulus here. But again, it's still not too close. But how can we translate this idea and materials research to the real application? That is the thing. So in order to do this, what they do is actually they use the alloy design framework. I mean, this so-called alloy by design for titanium. I mean, to borrow the concept here from the aerospace alloy design that can identify the phenomenon in the physics, what happened in the gamma beta stable superplasticity here. I mean, this is for, again, just emphasize it's not for implant, but borrow the concept from this one to optimize the low cost formable alloy with the, again, they call ABD still, alloy by design, with the cost, strength, stability, density, and formability here to find a new design space. Again, they use the same concept to consider cost of the material. Density should be not too dense and not too low, and then normalized diffusivity, strength of azimuth index to basically try to respond this. And then you map the new alloy composition by considering this into the design space here, and try to rank and also select some window that allow you to do some process specifically for the application you are looking at. So in this case, this is a superplastic forming in the fan turbine blade. So when we'll need a working window for this, they know. So this may not be able to apply directly to the implant, but there will be some example to show you. So let's say they know the window that give rise to the optimized condition for that. Again, this is based on engineering selection. It's not just the data as a data. You need to select this based on some physics-based understanding or physics-based modeling that allow you to select the right window to cast or to produce the material. And this actually, in the backbone of this one, we also run some model in the background. So that's why it's actually titanium 6.4. Looking at this since 2013 on the particle level, molecule level, microstructure, and macro scale. So we will combine the material by design here with the process by design. So we'll try to use the framework that I mentioned earlier, that we use the thermal fluid flow for the molecule, and then grain growth model to understand the microstructure, and hence another solid transformation as well. So give you some idea as a picture here. So if we apply previous one with additive, so we start optimize with DD process, for example, and looking at the microstructure evolution at the representative number of layers of deposition here for design a new material. And then we need to use this microstructure informed framework here, physics-based machine learning framework, to input the data to using thermoclock here, output as a, so we'll have input and output as a phase equilibrium or intermetallic transformation, temperature, solid solution strengthening, all the physical parameter that you are looking at. And then we input this process variable from whether or not you use PBF or DD, and then trying to use the a number of platforms, CFD, CA, DIGTRA, Prisma, to produce or to calculate the thermal cycle kinetics and then microstructure information. And after that, you use this microstructure information in terms of the everything you have as an input to use the property prediction platform to mechanical property. And that has to take into account the fact that this process is so kinetic. So we need to understand how different that we may anticipate it from the process before. For example, that what we talked before about freezing range or the change in the solute segregation will be considered. So that is the conceptual diagram that we try to draw here. Like you will not actually go to this pathway easily. Like in your alloy design, you may need to adjust your inside merit indexes, or basically the criteria that you use, considering these kinetics that are induced by the AM additive manufacturing processes as well. And this will feed into the alloy design or data-driven machine learning framework that mentioned earlier. And this is how we feedback or improve the model to design a new product. In our case, it will be new material, new powder, for example. So we also done some detailed characterization and simulation on this as well, on the single track single track of titanium alloy, and try to understand the alpha beta formation. And then you will see that this is very detailed, characterization and calculation. This is calculation, it's not characterization actually. This is calculated. And then in the 3 layers, so you can understand the effect of the kinetics and also microstructure development across the characteristic, I think, size of the process. So you can actually represent this into the design, alloy design model, and hopefully this will be able to improve the design algorithm and hope we can get better composition, for example, to to print better as well as to get better property. After that, we will combine it manufacturing and process design to understand the physical effect in LPBF using uniform powder distribution. So again, this model will be scaling up a little bit now using the interaction of the heat source and model. Maybe you will include the effect of porosity here as well into your study. And this representative model here will be simulated to understand better condition. And I think now I'm trying to show how to link toward digital twin or digital model that we're trying to use. So you will see here the point I want to make is that the length scale here is come from micrometer to about 1 centimeter here. And you see each voxel here that you deposit the material is actually 1 millimeter. So there is a 6 order of magnitude mismatch on the scale here. And how can we represent 1 millimeter with all the information in the lower length scale, 6 of magnitude lower? And this is an important question actually that we have to understand the melting process in the 1 millimeter length scale. That is the reason why we do 1 millimeter length scale on simulation. Otherwise, if you use the match of 250, but I don't, it's not, 1 millimeter is still too small actually for the big model, right? So 1 by 1 by 1 is still too small. And that is why this is how we choose the length scale of the problem. And even you deposit here, you will see that we need to implement some clever kind of, we call switching function that not assign the homogeneous property in the in the deposition voxel here. It has to be some distribution of property in that. We call property switching function. So we need to switch the property at each deposition here differently in order to take to account all the lower length scale information. Still, work is going on. It's not robust. It's not done yet. But we know people around the world, it's not just us, doing the same thing. So they may run crystal plasticity to develop this method in order to allow property to be predicted correctly in the large scale model. So this one, another way we call element birth method actually. So we extend the model here to predict stress and distortion in a component scale. You will see here there is some distortion in the element already. Did you notice that? It's not actually hexo anymore. So we try to incorporate this into the part distortion during deposition because this is the model that we use to digital twin, right? If this one run fast enough, that means in the same time as the way, but time in 3D printing is in microsecond. And how can we run this in microsecond to get the feedback into the digital model, physical model? That is the big challenge and question again. So we have mismatch, we bridge the length scale now, but the next question, how can we use this information and feed back into the physical model with the reasonable time? not in this time, so it's too large anyway. So now we try to bridge to this, but we need to feed back to that. So this is the kind of the real things that I think as an engineer has to work together. This is no way out. If you want to build a good predictive model that can do something or feedback some useful information. Otherwise, you may rely on the sensor data that you get. That means based on the sensor, the predictive capability based on what you measure. It's okay, it's fine. But if you want extra information which not easily measured by sensor, it's probably difficult, right? So you can do digital twin in many ways you want, actually. Or even you can do digital twin for example, I don't know, serial sectioning of something, which is not valuable. But what we do here is about mission critical part that we need to really take care of. And then this may be very expensive part as well. So again, there's some number of drawback and also some challenge, remain challenge that we need to do. So that's why it's still we still have to communicate with the data from the low length scale to the macro length scale, and then feed this data back and forth. This is maybe small loop control here. And then the new method here, taking into account the component distortion, and then you will see that is actually calculated, and also is actually taking into account here. So the material property is important in this case, because you need a function that can switch the property considering air and material and powder at the same time in a voxel or in a cell of calculation cell that you do. So again, people trying to do this and try to validate against experiment like we do, we show you a little bit later. So you will know that this will be good. If this geometry is not simple like this, if this is a turbine blade, how can we make sure that we predict something correctly? Otherwise, you will do the we call auto collection wrongly, and that's not good, right? That means you may try to produce something wrong in your critical mission part as well. So we will need to take into account of the lower length scale data. That's what I mean. But now today I'm trying to elaborate more what does it mean by that. So take microstructure data from lower length scale model to include the information to the part scale analysis here. So this is some two different methods that we mentioned that we call element birth and death. And then another one is, that means birth and death in one element assign one property. Another one is switching function. That means one element not homogeneous anymore. So you have assigned property into this one. And then we try to compare these two methods together in the part scale analysis. And this is the predicted thermal cycle in the, we do multi-layer deposition as well. So we want to make sure that we can see here the repeatability of thermal cycle in the real digital model we want. So we also validate this with experimental data. But as I mentioned to you earlier, this is the plate that we are looking at. This is the plate here. This is the plate here. So there will be bending. The curve of due to the distortion when you deposit the part. This is the size about 10 millimeter length scale, and this has been done since 2014, actually, so 10 years ago. And then we compare the thermal and distortion for the validation purpose. So we use the data from two methods, which is element birth, that means activate element by element, and also property switching. So we switch the function here. So you will see that property switching function get predicted temperature at the base using thermocouple measurement, very similar, very close to the experimental measurement here. So you will see the thermal cycle start to increase and then decrease like normal. But again, this is have to be noted that this is at the substrate, not in the melt pool. And resulting distortion has been measured based on the calculation and experiment here. You will see that switching function actually a little bit closer than another method. So this gives us some idea and direction to move forward in terms of how to develop this digital model that can capable to predict the part scale analysis there. So this is some initial work that I've done, and then because there is some other colleagues that involved in this kind of work, so I did not say this is all previous. This is not all my work. This is some other people work as well that we collaborate together to bridge the length scale or multi-scale, and then we hope that this kind of approach, as I think this thing is relevant to mechanical engineer as well, that will make us going to the right research direction. So this is more about digital twin using data from experiment and from the model to basically try to predict, to create a digital or predictive digital model that allow us to further develop for digital twin. Again, digital twin as a digital twin, I think is nothing without this brain, right? Otherwise, you don't have any capability to do anything. It's just a model to do something which anyone can do. I think. So material data, material information is so relevant. So moving to another, a little bit different, but I may call it material informatics, about the material discovery. It may be related topic as well, if you want, but it's not really digital twin per se, but just want to give you example that we discussed in the past few days about a new nickel-based superalloy that I'm talking about. I want to elaborate and share you some experience of our journey. I mean, 10, 15 years ago that we tried to develop this. What is the thought behind that? And I believe this is a little bit some history that what we do. So I actually previously I was in the part of the alloy by design for the new nickel-based superalloy here for additive manufacturing. So we published the work after a number of years of work in Acta Materia on the alloy by design application to new superalloy for additive manufacturing. The work, this would be a kind of outline of the work here that we do. For example, we call material discovery or material informatics, whatsoever people call it now, but 10 years ago, there is no such a bad word like this. But anyway, 3D printing for material here. We're talking about a several type of material, right? This is about the 4 class of the material we're talking about this day. And this is important because people talking more now about material discovery, material informatics, and that actually what we are doing 10, 12 years ago. So based on what this concept, I share with you the journey, what we do. So we know I will start with background and motivation and challenge in additive manufacturing based on our understanding that time, 2013, 2012. And then we try to use process. We know that it's a process-sensitive manufacturing. So we use the process-informed design here. And again, have to know that based on the availability of data that time that we have, and we try to design for process, microstructure, and property. Again, in order to close the loop of the PSP, which is processing structure property relation. So this is a bit repetition from previous slide that you've seen before, that I highlight the output, but this is a bit the underlying thought that we hypothesize that we need a new class of material for the new processing approach that we use. So every time we have a new process like forming, casting, or additive manufacturing, whether or not we can use the same material, that is the hypothesis there. And then we said AM will be enabled by development of new generation material. In this case, we're interested in nickel-based superalloy. And then that is another previous slide as well. You will see that there's some challenge because this is a rapid repeat thermal cycle process that may induce defect, locally, and then non-equilibrium things can happen. So the challenge is try to control microstructure by processing parameter or processing root here. And we hope that we can reduce some, or we get some property we want, not necessarily to be defect, but about the performing material that can be used for additive manufacturing. So inspired by the performance of alloy that you may see, the AM reduced the creep right by about 1 Lassen-Miller parameter. If you see here, it shows from CM247, which is single crystal superalloy here, 1 order of magnitude. When you change from directional solidification, you will get lower of the creep life here in the Lassen-Miller plot here. And then if you try to do some, additive manufacturing in the same material, the creep life actually reduced further to this So based on available data at that time, and then we compare with MA, MA. This is a cast alloy, which is somewhere in the middle. But if you talk about CM to inclined 7 to 1/8 in a rod and AM, it's the same. So the life of the material after printed, again, this is actually as print machine condition, machine at print sample, yeah. So there will be some difference. So another thing is the role of the processing of alloy performance. As you know, they're so very heavily textured based on the observation that everyone knows. Isotropic property is all around, and there's some common defect. That time we don't know, we don't investigate totally much on this very much. So lack of fusion, cracking, or porosity usually found in this kind of printing process. And then we try to consider residual stress as well in the new alloy that we're going to form, because as I said, we need to predict some way somehow, or have some parameter to indicate what happened after processing this material, like strain edge, cracking, that relevant. That is why. So we try to, based on observation here, the strong texture and residual stress are built up during the process. So what we do, we try to print this nickel-based superalloy in the condition that we believe that is the optimum condition. But still, it's actually, you found a lot of crack here. That, again, I will show you later. We developed this alloy based on the Lenarshaw 400 AM machine. So you will see that it's still uncoverable. Interregular cracking is a more critical challenge for this time. Temperature-dependent property here, and cracking found occur everywhere. We don't know very much at that time because what happened, but further investigation has been investigated later. That I showed you yesterday, that solidification cracking try to classify what type of cracking during the material printing here, and residual stress. As well, we done some residual stress experiment and measurement using the bridges structure. So the critical challenge here, we believe the residual stress is facilitate the crack formation at grain boundary, and at the edge, also at the bulk of the material. And then, as you know, if we keep this in mind, in order to develop a new composition, we need to look back a little bit about what we need. And this composition is supposed to use in the high temperature application. As we all know, this is for high temperature. It's not some when I say high temperature, it's performed at least above 850 degrees centigrade or above 1000 degrees centigrade. And then we're focusing on the critical part like disc or blade material. If not single crystal blade, it will be some other blade made from inclined 718. And traditionally, we use casting, and this is a kind of composition of the available, and also based on the benchmark actually of the nickel-based superalloy we are considered. So you will see it's about 13, 14 elements that form one alloy system. So this slide, I think I may script this slide already. So this is important. So what we do, the chemical complexity of nickel-based superalloy is an issue. So it's contained up to 13 elements, and limited information related to composition property trade-off are available in literature. There's not much in literature about this, especially information about the damage characteristic in limited number of alloy. It's just CM247, Hastelloy, Inconel 625, Inconel 718, and etc. And that means if you want to vary the composition, I said, if the resolution is 1 weight %, if you have only 2 alloy elements, you already have all 1,000 element choice that you can choose. But if your resolution is 1 weight %, but 6 principal elements, you will have about 1 billion choice to choose. But again, if your resolution, because in nickel-based superalloy is 0.01% is significant to the property. So you may end up with 10 to the power 21 composition. How can we deal with this? I mean, this is already big data for me, if not 100 trillion. I think this is more than trillion, several trillion composition. And the data that we can find from literature is so limited at that time. At that time, there's not much paper that you can find from the Scopus database here. So it's just thousands of paper only in the number of AM material. I'm talking about AM metal, AM data that we can find that time. So how can we do this? So this one will need to base on some empirical design. That time we don't do any fancy modeling yet, but we do to some extent. So what we do, we have alloy by design here. So this is a bit material informatics, and then you feed into the small batch of the powder that you can produce. You atomize it, and then you understand the thermal fluid dynamics, I mean the melting, and then we use this machine to optimize. We use a reduced volume build, so with the minimum 1.5 kilo of a new powder that we can use, and then we accelerate the testing by the facility at Oxford to validate the model and then close the loop of the design of the new material. Again, this is a kind of material discovery framework that has been done long time. Modeling, we use kind of modeling in form, but modeling in different length scale from empirical to the physics base, to the alloy development cycle. And this is the alloy composition here we consider with the major property that we can have: creep resistance, oxidation resistance, manufacturability, density, and then material cost, because cost is a big factor for the new design, right? You need to take into account to that. And you have the composition material property relation. But alloy by design framework is a bit different. So we want to understand the design constraint here backward. So, and then we want to work out what is a composition that gives rise to this property. Kind of inward design. In order to calculate this one, we need to design alloy space, calculation of phase equilibrium, calculation of microstructure architecture, that time we call, identify the merit indexes, apply design constraint, and try out some set of design, some set of composition in order to eliminate some trial and error. And that is something we said. This will need to take into account the strength of material, which link to the ABD energy and gamma prime fraction, which is some question before. This may calculate from first principle calculation with the new composition of material. Again, we link the lower length scale to the alloy design or material informatics here. So you will see this is, if you're not in the metallurgy field, I may explain a little bit more. This material is going to be, has some architecture like this. So gamma prime with different crystallographic structure, kind of cuboidal structure here, which is quite amazing, very ordered structure in the material. And the map here show the composition. And you will see that the activity of the slip system is ABD, antiphase boundary energy, will be on this a slip plane here, and the composition dependent of gamma prime actually has been very important to the strengthening of the material, and that's why this will be considered in alloy design cycle as well, the strength of material. And then we identify the strength of material using these indexes. So you have ABD, which is probably calculated from somewhere else, and then because you need to feed into the design loop every time when you get a new composition. So you have to calculate every time here. Fraction of gamma prime, again, there's some empirical equation you can use, feed back into this, and then you can get different fraction and map different energy here in order to define the strength of the material. And this strength of the material doesn't need to be excessive amount of gamma prime, actually. People may think that the more gamma prime, yes, the more strength, that's correct, but we have to find optimum condition to get enough, let's say in composite, not need to be a lot of fiber to get the strength that you want. You may need to find a minimum, upper bound of the minimum level of gamma prime that gives the strength that you require. And next one is consider the process. That time we consider, this is the graph that we conceptually draw, and then you see this happen at this stage. This happen at this stage after heat treatment or doing aging step. And the strength of this will susceptible to fracture. So the fracture or the failure of material need to be considered in the alloy design cycle as well, or we call informatics, whatsoever you call, for additive manufacturing system. So there is that's how I said yesterday about the Incal 718. So we start from what we have, and then based on what we have, we believe in the weldability diagram, but we know that it doesn't have anything doing with the additive manufacturing. But we borrow this concept and we assume that this additive manufacturability actually similar, I would say, to weldability, and this is a big assumption. That's why we follow this kind of diagram to develop some indices for the crack. And then we use crack formation due to the shrinkage as a cooling and precipitation hardening to consider into the design cycle. And then the rate of gamma prime precipitation influenced by the fraction of it. And then the growth, again, you will see here that is based on the metallurgy. We can call that, this is a physics-based informed machine learning that we try to develop here. And then the next attempt, we modify that diagram a little bit. And then we try to say that we want to use this diagram for additive manufacturing. That is starting point of the link composition and processing. And that's we call this criteria as a cracking criteria, as the criteria to determine manufacturability of the material. So we use this one to indicate by the, actually we cannot incorporate at that time thermal signature into the process, but we use these indices that I showed you yesterday to take to account, okay, this may be the crack will define the manufacturability of the process, and this diagram has been proposed. So you can find it in the paper as well if you want. And then that means we can isolate high strength alloy for AM. This is the very first version, and that time this company that I'm collaborate with doesn't call alloy. If you may know there's a company called alloy now, but previously it's called Oxmed. The first generation, you can identify the low and high crack susceptibility. And then this is actually trade-off between resistance to, we still call well cracking, not AM, and high temperature strength. And that is, we need to consider another factor of certification. Cost, big factor. Oxidation, thermal diffusivity, density, fatigue resistance, thermal expansion in the design cycle loop, in the material informatics loop here. And then we can generate the different ranking at different, because the screening of this based on the metallurgy that we identify the window for different, let's say this is a more mass fraction of gamma prime at 900 with strain edge cracking. Strain edge cracking, because we're talking about cracking at that time, and thermal temperature, creep life at 1000 degrees centigrade at 137 megapascal. And this, again, there's so many indices that we use to screen out and then identify the window for the new composition that we want. So this is how the alloy design framework has been created. And then all of these results here, you can find it in literature. And next is about once we get that composition, what we can do, how we do it. We need to prototype this alloy manufacture using atomization, right? So you will know that this is basically alloy composition that manufacture using gas atomization. We use the industrial practice atomization to produce the new composition that we found. And then at that time, we all know already the hurdle for this processing. You have trap porosity, microstructure, even dendrites, something like this. And then we run simple. That time it's not very fancy, simple, but give enough information for us to know importance of the parameter of processability to the new alloy that we are going to develop in terms of porosity that may lead to crack or surface morphology at different conditions compared with traditional alloy. And we then do the printing basically at a selected condition, and using this, as I said, it's developed using Renishaw ABD alloy series using Renishaw AM400. So I think every time when people talk, I have to mention about machine, because AM is a machine-dependent process. Which machine you develop this alloy, you will need to use that. Yeah, so basically we can get the best processing window, and that is the best condition up to now. Just want to feedback. I hope this is a closed loop control. Feedback to yesterday talk that is the condition we use to print those 4 alloy to study the cracking, if you remember. Yeah, so we print this and model to inform the choice of process parameter. Again, you will appreciate that this is not just happened by chance. It's actually very well systematic. At that time, we do some simple grain growth model as well to understand the microstructure of the function of the parameter that we optimize. And then we check the printed condition. Again, this involves not only modeling, but also a lot of experimentation that you can see what happened. And then we found that time that there is no gamma prime forming in this new series of the new composition we're looking at. So it's supposed to have at nominal composition at 25% gamma prime, but we found no gamma prime during even prior to heat treatment as printed condition. A solid solution. And then why the new alloy is actually manufacturable. This is the question. That's the beginning of the work of in the following work actually that we do. So you can know. I mean, I don't need to repeat what I said yesterday. I think you will see there's no crack, and then we try to understand why. Again, the structure is localized. That's what we want to say. Grain size in new alloy is smaller, and random texture, actually, which is better than columnar grains, is not preferred. And then less geometrically necessary dislocation density, I mean, in the material. And this actually contribute from the eutectic acetic cracking. That's why I'm asking you in the carbide cracking. That time we haven't identified very much, but no metallurgical phase as well in this new alloy system compared without aging. But the CM247 is a lot of problematic at length scale that we're talking about yesterday. You find some liquation, liquid film, carbide, gamma prime eutectic in the unaged sample. And this first generation here, once heat treated, you can actually recover back the gamma prime certificate, and carbide has been observed after heat treatment of this new alloy here. I mean, we use a atom probe to really map the composition in 3D, what happened. So there's isosurface of carbon, chromium, and aluminum atom itself in this one. So it starts to form gamma prime, and this is what the gamma prime that I show you is not defect. This is a gamma prime after heat treatment, actually. So you will see not only primary gamma prime, you see a secondary as well. But anyway, this needs to get the right heat treatment protocol to basically homogenize the structure later. But I leave that for other talk. It's not for this one. But anyway, if you see the property of these two new generation as printed and heat treated, then you will see it's involved a lot of testing you will see that as printed condition, the strength of this can be recovered by heat treatment. I mean, at the as you know, this is anomaly. The stress here is this is the typical shape of nickel-based superalloy stress at high temperature, but yeah, it's recovered back due to the gamma prime precipitation. And this actually map back to the very first slide. That strength and creep property of this has been improved by, I mean, is quite close to CM247 in AM, but still not very matched to the 718 yet. But please note this point. I will talk to you a little bit more. This is 0.2% proof stress of the first generation alloy. And this is what is it here in terms of creep life. It's actually better than CM247. So, but it's performed about the same temperature capability. But this one also not print easy as well. I mean, 718, because this is a gamma double prime strengthening material. And in terms of the second generation, we do the same. And you will see the green line here. At 900 is printable and is actually performed better than the first generation series that you can see without crack, the same. And the second generation also no crack and with improved property. So the performance of the material go up to 900 centigrade. And then we also doing hardness and distortion for this new material as well. So hardness with as heat treated and as printed, you will see the hardness is covered back compare against several material here. So we in second generation we also have several series of the material, and then we also do the bridges structure to characterize the distortion in as fabricated or as printed condition for the number of alloy, and you will see that the new alloy actually has minimum distortion compared with other two. Like CM247 is open up significantly 5 millimeter here, and then in 718, for example. So we then now need to think another factor, as I mentioned earlier as well, because if this AM actually apply to the thin wall structure, the property will be different again. So that is so many factors we need to consider. The effect of material, if there is no side effect, it will be like this. But if no side effect, will be strength will be uniform, right? But with the side effect, the wall thickness is actually affect your property. Again, you need to take this into the alloy design consideration. Yeah, with the thick section here, if you want to print this part, this is the kind of part of something, I think bicycle or something like that. Again, you will get the very low surface to volume ratio and M surface finish. In this case, we assume not relevant at this stage. So we characterize in terms of the side effect. I mean, this data is size-4, but we also do for a particular application. We didn't show it here, but you will see smaller, you get very low strength and ductility. With the larger, you get better strength, but again, you can customize your your property based on the size, and this is really important information to consider in mechanical simulation and also design for the application that you are looking at. So basically, just want to summarize here. So development of alloy is just because we want to develop a new composition that get the manufacturability that can be processable with the increased operation in temperature and decrease in crack density. And you will see that the performance of Inclin 718 is not actually ideal anymore. So we need to find a better material that sit here with additive manufacturability and also reduce crack susceptibility as well. So the performance at the temperature, at this critical temperature here, give rise to the different generation. I think now we have 4 or 5 alloy company, I mean, with the new generation of high temperature application. And with that, I think this is just I want to mention something that this is not relevant for nickel, but just to show that the impact of this definitely all directly will be powder feedstock company, right? Which there are a lot of company doing on that in Germany, in UK, in USA. And then we also influence this one for a number of applications like energy, nuclear, and this is definitely all high temperature 3D printed part that are available now, even in SpaceX, X1, GE, NASA. So with that, just want to summarize the talk. This alloy by design approach is not rely upon not only empirical development of the bucket chemistry or statistical model. It had to use compositionally isolate high-performance engineered alloy specifically for additive manufacturing. And alloy composition affect the melt pool geometry, as you see before, subsequent grain structure, and suggesting that different processability are required for different alloy. The AM microstructure localized depend on the process condition used and thermophysical property. Effect of composition on processing microstructure can be predicted using compositional tool on the right length scale. Again, the length scale is important. Solid solution of the new additive manufacturing alloy has been observed in the as printed condition with no secondary phase gamma prime. But after homogenization, we recover back the strength of the material. And then this AM process informed alloy by design approach exhibits a good balance of design of critical property, resulting in crack-free, high-strength, printable superalloy. So that is the ideal things we want. But again, we need to add another bit with targeted application as well. That is the key. So with that, I think thank you very much. Just not because all this presentation finished, but for the whole course for us today, for this week as well. Thank you very much. Just want to ask you have any question before we, I think it's probably 10 minutes, right? 10 something, 10, 15 minutes.
Sir, can you go back to the size effect slide?
Which slide?
Size effect. Strength as next.
Yeah.
Yes, sir. Yeah. So, what is the reason for reduction in the strength? You said size effect. Is it because of the variation in the microstructure, or?
Yes. I think I have a slide yesterday showing the columnar grains and the trap of some feature in the microstructure. The smaller, I think this is for yesterday, that I have a diagram showing that, and that affect into the property.
Okay, so can we enhance it by doing post-treatment?
That is something we haven't. I think in this one is titanium 64. There is a dedicated paper for this one. I think I can't remember that. This is not my work anyway. It's my colleague. So you may looking at that. But this is Thai 64. That means after post-treatment, even that is columnar grain ply beta. Yeah, I have to say it's different from nickel-based superalloy structure. So I'm not sure. Probably yes. Probably yes. Probably yes. Yeah. But they do both as fabricated and as heat treated. That paper is probably in Acta Biomaterialia, or by material and design, something like that. Yeah. Back in 2014, 15 as well. So 10 years ago. Yeah. I think, but on top of my head, probably a little bit, not a lot. It doesn't, yeah. But again, that is based on Thai 64. It's not nickel-based superalloy. If you want, you can design for nickel-based superalloy. But because why we can do this kind of small testing like this, at University of Oxford, they have the ETMT. Yeah, electrical thermomechanical testing, right? Yeah. So they can deal with the miniature tensile test pieces.
Micro tensile.
Yeah. No, ETMT. I think electrical thermomechanical. Yeah. If I may be wrong, but yeah. But it's the abbreviation ETMT. You can use digital correlation, DIC camera, to look at the strain development during testing as well. That's what they operate on the machine as well. Yeah. You can go back to the paper. I think the first author is Dr. Enrique Arabord. Yeah, he is a co-founder of the company as well. I'm not. Any other question? Yes, sure.
Yeah, Professor, thank you very much for a wonderful presentation. It's very insightful and inspiring also to look at this. I just have a few questions. This regarding the length scale you are emphasizing on the 1 mm, and
Okay.
then you translated it to the macro scale. I could not get it. So
It's another way around from micro to macro. Yeah.
right.
We upscale.
So you were saying 6 orders of magnitude you were upscaling.
Yeah, from 10 to power minus 6 to 10 to 2 millimeter scale. So I'm talking about component scale.
Component scale. So it's 3 to 4 orders, right? Because 10 power minus 6 meter to you are going up to 1 mm. Because you were doing it 1 mm.
But our target is to target something 0 centimeter scale.
Okay.
So 10 centimeter, again, you can say 4 or 5, yeah.
Yeah, so your intention was to do the micro scale molding at 1 mm length scale so
Yes.
that the output can be easily translated at the macro scale, because your element size is 1 mm even in the macro scale model. Is it what you are telling?
The element size in the macro scale is 1 millimeter.
1 millimeter. So even at the micro scale level also you are taking
1
the length
millimeter.
scale up to 1 mm so that the output parameters can be easily translated into this.
That is the idea.
That's what.
But 1 mm in Melpool, if you 1 by 1, you will have to scan probably 100 or 50 layer, which is impossible in the Melpool simulation as well.
Right, right.
So there will need to be some way. but you're right. In terms of length, we try to capture 1 mm.
Okay.
And that you see a lot of paper. It's not just my paper.
Right, right.
A lot of paper looking at that and try to find some way to link this information across scale. Yeah.
Yeah. Okay.
Thank you. Yeah.
Actually, so when we talk about the part scale model, but during the part scale model, typically we have, generally simulate just a layer in context of making a cubical sample or like that, right? But the geometry of the part itself, when it becomes complicated,
Yes.
there are down facing surface, there are up facing surface, there are curvatures, everything. So those geometrical effects, in order to incorporate those geometrical effects into the macro scale model, is it possible right now, or it's because those
that is the criticism for funder. Everything what the AM5 is used in the real application. But I think, as I said, it's about the application that you identify. If this part is for small part, it's not big part, but complicated shape, that I think that is a targeted application we look at.
yes, because
So that means it's not going to be a bulky, it has to be delicate
because
component,
if
right?
if the modeling, it's a macro scale model is in context of simple cubical samples. If we prepare the micro scale model, I can trust that okay, it might be giving some correct result, but there are companies who are for complicated shape itself, they are developing the part scale model.
Yes.
And they are claiming that the stresses and are comparable to the actual building, means what this stresses we
But
also
first,
building.
I have two point to say. first is actually, again, the part that you're looking at not going to be bulky or simple shape. It has to be delicate part. Second is about statistic. So AM is statistical, the statistical data from modeling from experiment will be used, incorporate with the macro global model from mechanical field. So if we assume that, assume again, the stress is universal across this geometry. So we may use that state in this one to tell something. If you know the mechanical field of that part, I'm not sure, again, this is something probably thermomechanical people, mechanical engineer has to find a way to homogenize this way to scale this up to mechanical field that you're saying. Yeah. But otherwise, I don't see the way out for this one. So we cannot actually measure every single condition for that, right? For sure. But we need to find a way more representative to what you just mentioned. And then I hope there would be some success case or some example that we can use to prove this concept. But so far, I haven't seen it as
But
well to link.
there are companies that claim that software is able to measure for complex component as well the mechanical fields they can measure. Stress field,
Everyone can claim, yeah.
but
I don't know. They may want you to buy their product, I think. Any other question? Yeah. Yes, sure.
Relating with your yesterday's lecture on the solute trapping. So,
Okay.
what is the exact cause of this not formation of gamma prime in the ABD alloy? Though the thermal signature is reaching the solver's temperature multiple times, you don't see formation of gamma prime. Is really
I
surprising.
think from the solute transport or solute trapping and micro segregation study that we do, we understand that there are few factors that new alloy don't have, because the way that ABD algorithm here select the alloy, they screen out the highly segregated element like hafnium, carbon, and whatsoever I showed you yesterday.
Titanium, aluminum.
So that I'm not sure it's coincident or not, but it seems that they don't select this for the new alloy composition, or probably with cost as well. And that's why you get in the segregation profile, you get the homogenized kind of uniform or average segregation profile. There is no preferred segregation or selective segregation. So that's what we found from that work. But CM247 LC or Incal 718, they have preferred. As you know, you evident a lot.
Yeah, we have also done that. There is preferred segregation. There is formation of gamma double prime also in the as printed state.
Yes. You mean
In the as printed state,
there
is
which material?
IN 718.
Yeah, of course. We see it from casting, from additive. We seen that. Yes.
But it's a total surprise that you don't see the formation of gamma
Yeah,
prime.
that's because our justification from that paper, Nature Com paper yesterday, that we don't have kind of harmful element for that segregation transport. Yeah.
during this recent time you are preferring to have the gamma prime segregated during heat treatment.
Yeah, that's what I said. We call it print soft, and then we recover the strength later, or harden later.
At the time of printing, it is
Solid solution.
It can cause crackings and all, but later
No.
on, at the time of printing, if gamma prime is precipitated, it can cause cracking, right?
At the time of,
At the time of printing means when we are printing the samples.
if it's solid solution, probably less likely.
Okay. Yes.
But if it has some non-equilibrium big or segregation or solute profile, that may cause some impact. Because just a short period of time, you can actually generate how to say, a big residual stress because the element segregated to the boundary, and this may cause the cracking. Because as you know, you're not printing only one layer, you're printing several of thousand layers. Some layer below that may be already, we call intrinsic heat treatment. It's heat treated somehow already. So that's why at some point you will get some effective ductility dip due to that underneath thermal cycle. So that's why below that. But what we see is that the segregation here actually stop it. The crack is, I mean, I'm talking about yesterday talk, it stopped at the solute trapping zone. So that means there will be, that's why we hypothesize this may be some role into to stop or eliminate the crack. That's how we try to hypothesize. And that's why in the new alloy system, this segregation is actually not concentrated, but it's uniformly, but we call solid solution, right? It's solid solution in the material. So that's why there is no preferred segregation as printed in soft condition.
There no preferred segregation, there is no segregation. Everything is there in the solid solution.
I would say minimum, just for the sake of science here. Possibility is low. Okay, I think we probably call it, and then thank you very much. I will be here anyway until the end of the course here. Thank you. And next will be Professor Kumar for his talk. Thank you very much. Oh, it's used. Take away. After break.
Couple of announcements. One thing is regarding the feedback form, which we are going to circulate now. Yeah, that